Stanford University.
I want to start off with some generalities before I get to the nuclear business. We're in an academic place here. And in an academic place like this, we're full of experts, people who can tell you all the details about this and that and the other thing. And I think a lot of us don't recognize how confused the general public is. The general public gets confused partly because the media love controversy, and what the media usually puts up before the general public are what I call the deniers at one end and the exaggerators at the other end. The deniers say global warming is all a fake and it's a conspiracy on the scientists to get more money so they can do more research. And the exaggerators say the sky is falling, and if we don't change our entire lifestyle and turn the whole economy upside down in the next 5 years, we're all going to be doomed. That leaves the public in a kind of a confused state. And what I wrote this book for is I wrote it for the public to go tell them in a direct and scientifically correct but non-technical fashion what we really know, what the uncertainties are, how long it will take to resolve the uncertainties, what our options are in technology, what our options are in policy. It is very hard for any of us to say what technology is going to be like 50 years from now. So to say that we have to do everything with the renewables or the nuclear or what have you that we know now is really not the right way to proceed. The right way to proceed, as far as I'm concerned, is to take the most cost-effective way to make massive reductions in emissions and start to apply them. This gets me crosswise with a lot of my friends. For example, if you look at California's million solar roof project, sounds good, but you could reduce greenhouse gas emissions by twice as much for 10% of the cost simply by converting the Four Corners coal-fired power plant from coal to natural gas. We don't give any encouragement to do that sort of thing. We give lots of encouragements to things that are going to be important, but are small now, are growing, but are going to remain small for a long time. And we do all sorts of things that really make no sense. Now, a lot of people here know about biofuels and know how ridiculous it is to talk about corn ethanol as a way of reducing greenhouse gas emissions. Yet corn ethanol gets huge subsidies from our government. It gets those subsidies for political reasons. It gets those subsidies to get the votes from the Corn Belt. And if one party says, I'm going to get the votes from the Corn Belt by giving subsidies to corn, the other party is going to jump in and say, I'm going to get it too, so we're both going to do this together, and neither of us is going to get an advantage, but we'll end up putting a lot of money out into things that don't do any good. So the public's got a big problem. And even the students here who aren't techies have the same kind of problem. What should they really believe? In the climate at this university, I think you'll find very few of them who say that they are really among the deniers, but I bet you find a lot of them who would say, if you got them to talk honestly, that they don't really understand why this is such a big problem. So what do we know? We know that if we go on with business as usual, the Intergovernmental Panel on Climate Change says the average world temperature is going to go up by between 4 and 12 degrees Fahrenheit. That's an enormous increase even for the average. The high end of it is going to be really societally very disruptive. The low end of it is going to be very uncomfortable. And it's going to take us some time to work this out, and it's going to take us 20 or 30 years, I believe, to know whether it goes toward the low end or to the high end. But that's no excuse not to start working on this problem now in the most cost-effective fashion. It is a lot easier to keep CO2 concentrations at a reasonable level if you start while they're small than if you wait till they're big and you try and bring them down again. So when you're thinking about the climate change problem, you're thinking about where we're going and what we ought to be doing, you ought to be thinking about that issue. It's not, I'm not going to feel a pain from this. My granddaughters are going to feel the pain. And there you have a real problem in a decentralized democracy like this one. The consequences are 100 years from now, but the most effective time to start working on this is now. And now it's very easy to say, well, if we wait another 5 or 10 years, it's not going to make much difference. That's what we all have to counteract, and that's what we have to do. We also have a big problem with the rest of the world. Unfortunately, energy use is coupled to economic development. Everybody knows that. The poor countries want to get rich. The rich countries don't want to get poor. And so energy use is going to go up. How do we do something that allows growth in the developing countries at the same time we control greenhouse gas emissions? That's really a tough one. And I have to confess, I do a lot of hand-waving at the end of the book on that issue. And one of the things I learned in writing this and looking at these issues is that politics is a lot tougher than physics is. So with that, let me now start off and try and figure out how to make this thing go. There. Here's some things that I learned in a long time of working on various policy issues. So there are the Richter's laws. The future's hard to predict because it hasn't happened yet. That sounds like Yogi Berra, but it's really mine. No matter how good a solution is, some will demand we wait for a better one. I call this rampant utopianism. We need utopia to do things. Short-term pain is a deterrent to action, no matter how much good that action will do in the long term, and the largest subsidies go to the least effective technology. And we all know that, and I already gave you the big example there. That is corn ethanol. So if you look now at the energy supply of the world, does this thing have a laser in it too?
Yeah, it should.
I'm worried that if I push that's just what I worried about. Okay, there's the right button. So you can see that this is total primary energy supply. It's the energy content of the fuel. We do things in a very funny way. For these things, it's primary energy, and for all of these things, it's output. So here, before you get to use it, there's a big efficiency. Well, from these things, we're talking straight about output, but you can see the biggest one is oil, coal next, natural gas, nuclear power, so forth. You swear this is a better one, huh? Well, I think I'll stick with this. I'll take the risk. I'm going to leave dangerously. No, if I may drop it. So when we talk about combustibles, we're talking about the fuel used by the poorest people. The poorest people gather up wood, gather up plants, gather up cattle dung, and they burn it. And those combustibles don't have any emission because everything that went into the carbon in them came out of the atmosphere. It's only when you start adding fertilizer and tractors and transportation and all that stuff that we get emissions. And other, down here at the very bottom, this includes all the renewables, all of them. They're negligible now. I said earlier that we got a problem in bringing the developing nations into this. This is a projection of what's going to happen in the next 100 years under the business as usual scenario. And if you like the IPCC stuff, it's very close to A1FI, A1 fossil intensive. That's the business as usual scenario. Most of the growth in the century is in the developing countries, not in the present, the industrialized countries. If you look at this and the industrialized countries stopped emitting greenhouse gases entirely, we'd still be in big trouble. So we have to, when we're thinking about this, develop technologies that are applicable to the developing world as well as to our own world. That's an important consideration. Is business as usual going to happen? Almost certainly not. It's not, because the price of oil is going to go through the roof, and coal is going to end up being in short supply if this sort of growth goes on through the 100 years. But we need solutions that can be applied elsewhere. These are the IPCC predictions. I put them in so those of you who want to look at this on iTunes or wherever Stanford posts them can see what they are. You get the temperature ranges, and there are lots of issues here. And as I said, there's lots of uncertainty in it, and the uncertainty needs resolution. And the uncertainties are of a kind that in physics I would call systematic. They're not random. There are more than 20 models that are used to predict the future. All of those models are tuned to agree with the past. They all have knobs in them. I can make this one more important, that one more important. They're all tuned to agree with the past, and they all disagree on the future. And the spread you see here is a spread in models. And as time goes on, we're going to learn more, and those models are going to come closer and closer together. So if you want to look at decarbonization, what do we have to do? Well, in the United States, the biggest single source of emissions is electricity generation and transportation. Those are the two biggies. So if it's electricity, you've got to talk about fuel switching. So we talk about renewables like solar and wind and nuclear, as well as things like geothermal and hydroelectric. If you look at transportation, cars are incredibly inefficient when you look at what goes out of the gas tank into the wheels. The EPA estimate on the typical driving cycle is 12% of the energy in the gasoline goes to drive the wheels. That's really pretty terrible. So that's going to change with and buildings. We need efficiency. Industry needs efficiency. Agriculture is a wild card here, and nobody knows what to do about it. Worldwide, agriculture and land use change accounts for 20 to 30% of greenhouse gas emissions. If you're talking about reducing greenhouse gas emissions by the amounts people are talking about now, by 2050, you have to get at agriculture, and nobody knows how to do it. In the United States, it's much less. It's only about 10%. But there we are. This is an introduction to nuclear power. So why should we do nuclear power? There is a worldwide big increase in nuclear power. And if you look just at the United States, you would not understand this at all. There are now 435 power plants worldwide now, 28 under construction, and another 200 planned. Most of those planned are in Asia, but even Europe is moving back to nuclear. Italy, after Chernobyl, abandoned nuclear energy. They now are talking about building 5 nuclear power plants. Britain is going to start again. Sweden has decided not to shut down their plants. The only hardliner still saying let's phase out nuclear is Germany. but that's for political reasons, and we'll see what happens. The main attraction for nuclear in most of the world has nothing to do with greenhouse gas emissions. It has to do only with available energy. Energy's in short supply, energy's expensive. If you use coal, you do a lot of nasty emissions and hurt all sorts of things, and hurt your population too. Now, getting your electricity from nuclear does really some pretty remarkable things. I always said that France should be the poster child of the environmental movement here. CO2 intensity is what is the emission per unit of gross domestic product. So there you see the world, and there you see France. France gets 80% of its electricity from nuclear power, and it has half the emissions on the world. United States, by the way, and this thing is right at the world average. People who think nuclear is too expensive also should note that France's electricity is the cheapest in Europe. So when you're thinking about this, you should be thinking about large-scale electricity with almost no emissions and what that can do. So this is the fraction of electricity generated by fuel. Nuclear is now 20% in the US, 16% in the rest of the world. And one of the things I've already mentioned that you should keep in mind is natural gas is so much better than coal that we really should be switching. Big hydro is already heavily developed in most of the world except for Africa, and nuclear is growing like crazy. Now, how should you think about using nuclear power? Nuclear power is very capital expensive, very intensive. Build a big nuclear power plant, costs are something like $6,000 per kilowatt. Incidentally, that's the same as the cost of solar photovoltaics these days. But you should look at this, and if you're going to build something that's so capital intensive, what you want to do is you want to run it all the time. You want to produce as much electricity as you can because you want to pay the mortgage on all of that stuff. So if you look at this, this is California. It's a particular year. You see the big variations in use through the year and through the day of the week. And there's something called the base load. This is a suppressed zero down here. And it's about half of the peak. And people should think about nuclear energy as baseload power, not the kind that you turn on and off, because if you think of turning it on and off, you're going to find nuclear electricity getting to be unaffordable. If you look at solar and wind, you've got another problem. And if I look at solar, this is the output of a solar system, a photovoltaic system, from considering the fraction of output from the maximum, which is high noon at the brightest summer day. And if you look, you can find in DOE's Energy Information Administration a map of the United States, which says what is the average output of a solar system in various regions. And the highest region is, of course, the Southwest Desert, and it's 22% of capacity. So if I put in a kilowatt capacity system, and I say, averaged over the whole year, how much do I get? I don't get 8,000 hours times 1 kilowatt. I get 22% of that. That's the reason that solar electricity is so expensive. Wind. This is a very messy thing. This is 1 month of a big wind system in California. And if you look at it, you find days when there's practically no output. You find days when the output stays up. You find nothing that's constant. You find an average that looks like this. Wind has got a real problem, and there's really no good analysis of what to do about it. The big issue for solar and photovoltaic is energy storage. So any of you who want to solve the world's problems with wind and solar have got to think about how are you going to do energy storage, not the kind that you put in batteries. You need things that are measured in gigawatt weeks, not in megawatt hours. And if you look at what's talking about today, it's megawatt hours of storage, not gigawatt weeks. So if I had to advise any of you how to make the biggest impact on greenhouse gas emissions by using the renewables, I would say go to it and do storage. So let's switch all to nuclear, and here are what the problems are. The critics say that nuclear costs too much. They say that it's not safe, there are radiation and accidents. They say waste disposal is a problem, and they say the chance of weapons proliferation is too big. So let's look at these things, all of them. This is an analysis that's done by John Wyant and the Energy Modeling Forum at Stanford. So this is an analysis that's done for, I believe it was 2008, and it looks at what happens if you put a big tax on carbon emissions. So here you see, here you see coal over there, and that's what happens to, I think that's coal. No, that's nuclear. Nuclear. The second one is coal. So if you put this emissions thing on, it goes way up. The black is a capital cost. This other bar is operations and maintenance. If you look at natural gas, the biggest thing in natural gas is the fuel cost, but natural gas prices have come way down since this was done. And now if you look at solar voltaic, solar thermal electric, and wind, you find the problem here is the problem that the sun doesn't shine all the time, and you have to amortize your investment with the time that the sun shines. So as far as cost goes, nuclear is fine, and there are 3 new analyses. There's some references in here at the end if you want to look at them. One done by the National Academy of Sciences in their new study, one by MIT Energy Group, one by the DOE. They all say 6 to 8 cents a kilowatt hour for nuclear electricity. People wonder about life cycle emissions. So here are life cycle emissions. Now, what do life cycle emissions mean? It means I have to make the steel for the plant, and that emits greenhouse gases. I have to transport it. I have to mine whatever fuel I'm going to use. I have to refine it. I have to bring it in. So here's life cycle emissions per kilowatt hour. And you can see that as far as nuclear goes, nuclear and the renewables are all about the same. So that is not really a problem. One of the things that worries everybody is radiation. Natural radioactivity. When the Earth was formed 4.5 billion years ago, it got uranium in it, thorium, potassium, long-lived potassium. And so there's a natural radioactivity that we live in. Cosmic rays bombard us from space all the time. And if you look at the typical thing that the average US citizen gets, it's, I'll get this right eventually, 240 millirem per year. Never mind what a millirem is, just think of it as a relative measure. That's what humanity has evolved in. We live in that. One of the things that surprises everybody is that everybody is radioactive. You're radioactive because one of the things that is incorporated into all our bones is this potassium. Potassium has nothing to do with bomb tests. It was put into the planet when it condensed out of a solar nebula 4.5 billion years ago. It's a very long lifetime, and when we sort of build our bones, potassium, calcium, relatively related chemically, and we get 40 MR. A sixth of the natural comes from that. Skinny person gets less, heavy person gets more. If you're sitting next to a skinny person, you are getting more radiation than if you're sitting next to a not skinny person. So you might think about that one. Medical gives us more, and the nuclear power plants give you 0.004, 1/10,000th of what you get from your own body. Coal-fired power plant gives you about the same. Now everybody looks at that and says, well, that's if they're working right. What if they're not working right? And now there are two big accidents that came along. One is 3 Mile Island, and the other is Chernobyl, and their consequences are totally different. They're different because the reactors are built differently. This is a schematic of what a nuclear reactor looks like if it's built in Japan or the US or China or Europe. It's got a big containment building around it, this thing. And the reactor itself is a little thing in the middle there. The longer things are the steam generators. But if you look at this one, it's sort of schematic. That's the reactor, that's the steam generators. This is the containment building. So if something goes wrong in the US, the containment building is supposed to hold it, and that is what happened at 3 Mile Island. 3 Mile Island, the core melted. The core of the reactor actually melted down. It released all sorts of radioactive nastiness inside. Radioactive gases escaped from the reactor itself. Radioactive water leaked out, and very little got out of the containment building. The biggest exposure to anybody at 3 Mile Island was 100 MR. Remember, 240 is the natural, and typical for people close was 10 MR, sort of relatively negligible on a scale. The reason that 3 Mile Island makes such a big impact is a Jane Fonda movie called The China Syndrome. Now, all you students are too young to know about the China Syndrome movie, but the China Syndrome movie, the thesis was that a reactor ran away and the core melted, and this hot stuff melted down through the bottom of the reactor vessel and down through the bottom of the building, and it was going to melt its way down into the earth and come out in China, hence the China Syndrome. I don't know how Jane Fonda and the hero saved us all, but they did save us. But that movie came out 10 days after this happened, and it had a lot to do with the reaction. Chernobyl is a very different situation. That's the Chernobyl reactor building. There are 4 reactors at Chernobyl. You can see some of the other ones here. This is the building from the one that went crazy. They have no containment on their reactors, on this kind of reactor. And the other problem with it is it can become unstable in certain kinds of operating conditions. For some reason, they took it into that region and it ran away. This is not a nuclear explosion. This is a steam explosion. The reactor's output went up so fast that control rods couldn't move, and the superheated steam blew the roof off the reactor, blew the roof off the building, and spread the radiation far and wide. Those reactors have never been allowed in the West or in Asia. Strictly the old Soviet bloc. And the European Union and the US have contributed a lot of money to modify the reactors of that type in the old Soviet bloc and to shut down some of them. Another thing people talk about is health effects. Now, health effects you can argue about. This is the only comprehensive study I can find. It's a study, the reference is down there in the corner. It's a study done in Germany for conditions in Germany looking at various kinds of energy sources, and the units are per terawatt hour. So this is per equal electric output. It's supposed to include everything: mining the fuel, transporting the fuel, accidents on the roads with trucks that are involved in the pollution, all the rest of it. And if you go through all of this, what you will see is that the only thing better than nuclear is wind power in this analysis. This is including accidents. So per terawatt hour, accidents are very improbable. So if you think about this, you will see that nuclear is relatively safe compared to most of the others. This will be in the slides, and if you want to know about bronchitis and admission to hospitals and all the rest of it, it's there. But I thought this one is biggie, the number of deaths per terawatt hour. Spent fuel. Spent fuel. I always start talking about spent fuel by saying, love it or hate it, we have it. We have 60,000 tons of spent reactor fuel now. The current reactors now existing are going to produce another 60,000 tons of this stuff before they end their 60-year lifetime. We got to do something with it, and what to do with it is the big issue. The costs of taking care of this are built into the cost of nuclear power. Right now, for every kilowatt of nuclear electricity, every kilowatt hour of nuclear electricity, you pay 1/10 of a cent into the Federal Waste Disposal Fund, which now has something like $20 billion in it, and will totally have $50 billion over the lifetime of the reactors. And that fund is supposed to pay for disposing of spent fuel. In the United States, the law says that spent fuel becomes the property of the federal government, and it's the federal government's responsibility to put it away. But paying for putting it away is done by the users of nuclear electricity. So the utilities have to give the feds some money. Now, the Obama administration is starting over again. They're starting over again for political reasons. This has nothing to do with whether Yucca Mountain is safe or not safe. DOE did a very long analysis, submitted a application for license to the Nuclear Regulatory Commission. The Nuclear Regulatory Commission is the umpire here. They look at this and say, do we agree that this meets all the standards for containing radiation for 300,000 to 1 million years? That process had just started when the Obama administration pulled the plug on it, and the reason they pulled the plug is to help Harry Reid get reelected again, although I'm sure they would argue with me if I said that, but it's really true. So we're starting again, and we're looking at other options. Are there other options? Yes. Do we know what those options are? Yes. I would bet you that I could write the report that it's going to come from this Blue Ribbon Commission. I could do it all next week. Now, if somebody would bet me enough money, I would do it, and then we'd see what happens when the thing comes out. There are other ways of disposing of spent fuel other than Yucca Mountain, but is Yucca Mountain safe? Yucca Mountain's safe, I think. So what's in spent fuel? Well, if you look at it, it has fission fragments are 4% of it. This is where the really intense radiation comes from when it comes right out of the nuclear reactor. 95% of it is uranium. It's the same uranium that you took out of the ground when you mined it. You could put it back in the mines that you got it from, and it would be no different. 1% is this long-lived components. These are called the actinides. They're medium radioactive, but they live for a very long time. And so this is the problem. If all I had to worry about was this one, I would build things and people wouldn't worry about it. The Egyptians built pyramids that lasted 5,000 years. We could easily build pyramids that last 500 years and put this stuff away and just let it decay and not worry about it. So the actinides are the problem, and the actinides have one other problem too, but here's what the actual radiation looks like. Okay, so here's all of it. This one, the one that comes roaring down, this is the fission fragments. Enormous amount of radiation. But when you get out to the very long times, these are all these actinides. This is the stuff that's 1% of the fuel, and that's you got to keep out of the chain. So a minimum of 300,000 years longer. So that we took Yucca Mountain. Yucca Mountain is an interesting place if you like the high desert. It's kind of got an odd beauty to it. Congress said spent fuel disposal is a federal responsibility. In 1982, DOE was supposed to find 3 alternative sites. They did: Texas, Washington State, Nevada, Texas. George Herbert Walker Bush was vice president. Texas got axed from the list. Washington, Tom Foley was majority leader of the House. That got axed from the list. And Nevada was left. Did Nevada get treated unfairly? Absolutely. I never understood why the government didn't give Nevada a sweetener. We spent huge amounts of money on civilian things, and we should have come up with something for Nevada to make life better for them. What people are talking about now as alternatives is called closing the fuel cycle. If I could take this stuff and burn it up in a nuclear reactor, turn it into fission fragments, my problem goes away. I don't have to do 300,000 years anymore. If I just take the plutonium, the stuff of weapons, and do that, then I have 10,000 years. That's down a lot from 1,000,000 years. If I can get the minor actinides out too, then I'm down to a relatively short time. This is part of the R&D program that's going on worldwide. We have a very incoherent program in the United States. I think that it may be getting more coherent. There's a new roadmap for R&D that's come out of the DOE, and that roadmap looks at what we have to do this sort of thing. We are not the leader in this. Other countries are the leader, and we're going to see what actually happens. So the idea is that you take, I'm just going to use the bottom one here. The light water reactors put out fission fragments, actinides, etc. You separate out the bad stuff, put it in fast spectrum reactors, and go round and round the loop till it's all gone. Why fast spectrum? Because neutron spectrum and the standard light water reactors won't burn this stuff up. So we have no coherent plan. And whether the new plan will actually make it through Congress, we'll see. So proliferation is the last of the real problems, and it is a problem. Who are the proliferators? South Africa, Pakistan, and maybe Iran, making their weapons from uranium. This is called the front end of the fuel cycle. They have this enrichment facility in Iran. The question is, will they cheat? And instead of going to 4% uranium-235, which you want for a power plant, go to 90% for weapons. Who knows? Iran's protestations that this is pure civilian are rather hollow. I've been there. They hide things. They don't tell the IAEA the truth. And you'd have to be pretty much of a idealistic, I would say, jerk to believe their protestations. Plutonium comes from the back end of the fuel cycle, and you burn up uranium in a reactor. Part of the product is plutonium. The uranium doesn't fission and split, but it captures neutrons and becomes heavier elements. And plutonium is also the stuff of bombs. So the worry is when you separate out the plutonium to do this multiple cycle stuff, do you give people more of a chance to divert the plutonium into bombs too? That's a difficult route. A 1 gigawatt electric power plant needs 20 tons of natural uranium, 200 tons of natural uranium to make 20 tons of enriched fuel for each year. For weapons material, 1 ton of 4.5% sent to a clandestine enrichment plant would make you 1 bomb's worth. So if you divert 5%, you can do it. Back end of the fuel cycle is more complicated, and I think I'm running out of time, so I want to leave some time for questions. So let me skip ahead. Nuclear power's future, what's going on? It is growing in the rest of the world. Doesn't matter what the United States does. It is growing, and it is not only growing, it is growing in a route that involves separating out the plutonium and the minor actinides in the back end and recycling them in reactors. The fastest growth is in Asia, and they are not doing it for greenhouse gas reasons. Greenhouse gas reasons is a bonus. They're doing it for secure energy supply. Japan has no natural energy supplies at all. It has no significant coal, no significant oil, no significant natural gas, and it's too small to do all of its electricity generation by growing trees and burning them. So they're doing that, but in the process of doing that, they're also reducing greenhouse gas emissions. The US has up till now no long-term plan for nuclear energy, but one has just come out, and if you're interested in it, the nuclear energy website in the Department of Energy has what they call a roadmap, and you can now download and take a look at their strategic plan. All sorts of things are happening. The new thing is small modular reactors that don't take as much money to build as the giant ones. That's going to become rather popular. And we'll have to see where we go from here. But the United States right now, to the rest of the world, is all talk and no action. If we don't have any program, and if we don't participate in the nuclear world, nobody's going to pay any attention to us. People would like to pay attention to us. People acknowledge that we have the best operating nuclear plants in the world, where uptime is 92% last year, far better than anything else in the world. We are acknowledged to have the strongest and best regulatory system. You should go to that talk by the head of the Nuclear Regulatory Commission. We are very good, and people are interested in learning how to do things from us. But as far as how to build reactors, as far as how to handle the fuel, nobody's going to pay any attention to us unless we get into the act. So I think we should get into the act. And I didn't even know I had that one. Anyway, I'm going to skip that. I'm going to end by just telling you that there are a bunch of references that make things easy to read. And with that, let me quit and turn it over to you for questions.
So before I let Bert respond to questions, I have to admit to a lie. I claimed that the chairman of the Nuclear Regulatory Commission would speak next week, but that was wrong. It's actually May 18th, which is 2 weeks away. So mark your calendars on the right day, May 18th. Now, questions?
Bert, suppose we switched entirely to nuclear energy. Do we have enough fuel in the world, known stock to sustain these plants for an extended period?
Probably, and the question is how much you're going to pay for it. There is a huge amount of uranium in seawater, but it's very dilute. How much is it going to cost to separate it out? If you look at the low-cost uranium, there's enough so that you can handle all the reactors for this current century. If you look at mining techniques improving so that you can take your uranium from lower concentration ores on land or from the water, then you can last for very much longer. If you look at the history of mining, Lynn knows much more about this than I do. Historically, what we do is we keep going to lower concentration ores for anything, and the cost per kilogram of whatever you are stays constant. Will that happen with nuclear? I don't know the answer. One of the other alternatives is what's called breeder reactors, because we only use now the uranium-235. That is 0.7% of natural uranium. And with breeder reactors, what you can do is you can turn the U-238, the 99.3%, into usable fuel. So there are two paths now. Are we going to go the breeder path, or are we going to the lower concentration path? I don't know. And right back at the beginning, I said, I don't think anybody knows what the technology is going to be like 50 years from now. But we got 100 years worth with no problem.
So can you say a few more words on the Gen 4, where you think that really is, and how long does it plausibly take to get there?
Gen 4 is the next generation of nuclear reactors. There's something called the Gen 4 International Forum. There are, I think, 30 nations involved in it. They have a website. If you hit Google and you ask for Gen 4 International Forum, you will find it. And they've looked at the next generation of reactors. They've identified 6 as the most promising potential. And those range from high-temperature gas-cooled reactors to breeder reactors. There is a sort of a division of labor here as to which countries are going to do what. Gas-cooled is, in fact, being led by South Africa. The sodium-cooled is being led by France, with participation by Japan and us, although France and Japan have all the technology. So which of those is going to be the winner? I don't think anybody knows now. The first of the new generation of sodium reactors is supposed to come on in 2020. And the first of, let me call it the large-scale gas-cooled high-temperature reactors is supposed to come on about the same time.
Bert, you haven't mentioned nuclear fusion. Can you say something about whether the increasing energy?
Yes, I will. I will. I'm going to quote one of the most distinguished people in the fusion business who said many decades ago, nuclear fusion is 50 years in the future and will always be so. So what's going on in nuclear fusion? There's this big project that's going on, internationally funded, cited in France, called ITER, International Tokamak Experimental Reactor. That is a multi-billion-dollar project. It is supposed to produce real fusion power in something like 15 to 20 years from now. You've got to build it, and you've got to do a lot of experiments with it before you do it. There are some much smaller, commercially funded projects which are looking to generate fusion power on a smaller scale, and I don't know what's going to happen with those. But if ITER worked as it's supposed to work, and you look at the cycles of let's build ITER, let's run it, let's determine the right configuration, let's build a prototype power plant, and then let's build real ones, 50 years.
Right down here, then Steve in here, and then we'll do one more after that. And
$1,000 a kilowatt for a nuclear plant. Has there been a study of worldwide
of what the cost of nuclear plants that are being under construction. I've seen no information in the working press on what the real costs are. But that seems to me the biggest bottleneck, because $6 billion for a gigawatt is the asset of a big company. So the decision is a major step by an electricity company to decide to go.
The problem is that nothing's been built in the United States for a long time. So I went to Japan and Korea, and I looked at the last 7 reactors that have been turned on. If you turn that in, add in inflation and all of that, those reactors cost $2,800 a kilowatt, much less than people are talking about in the US. And in the US, we do not have the skilled workforce already, and things are going to be more expensive here. Generally, people are talking about what's called overnight costs. Overnight costs is, okay, I come up with a satchel full of money and say, here, give me a power plant. So it doesn't count interest and all that sort of stuff. People are talking about $5,000 to $7,000 a kilowatt in the US. And we're not going to be able to answer your question properly until we actually build a few. We need to get back into the business and see what happens. So the cost in other parts of the world is known, and I can get you can find yourself, if you look at the European Union has done a study of reactors in there too. All of that is what's in the estimates of 6 to 8 cents a kilowatt hour in the US, assuming loan guarantees and assuming no disastrous delays in construction. Construction in the US is expected to take longer. We're talking about 6 or 7 years to complete one versus 4 years in Japan or Korea. So all of that goes into the reason why it's more expensive here than there. But if we get into the business and build a lot of them, everybody expects the cost to come down to a uniform worldwide cost.
Yeah, I agree with you that cost effectiveness is an important criterion, as you said, not the only one. There are other factors, but I wanted to find out to what extent, when you did your comparison across the board, that the hidden subsidies were in each one of them. I mean, it costs something to run the Nuclear Regulatory Commission, to run Yucca Mountain, the Price-Anderson Act, which limits liability. Supposing nuclear companies had to actually buy that insurance in Lloyd's of London. Would that significantly change the cost figures relative to the other?
According to John Wyant, who did this, I did not do that analysis. His analysis is the all-in cost of power generation. Now, that does not include the cost of running the NRC. It does include the cost of Yucca Mountain, because remember, that's built in to the price of nuclear electricity. If you talk to people about the Price-Anderson Act, they say the Price-Anderson Act is not a subsidy. What the Price-Anderson Act does is it says if there's really a disaster that costs more than the insurance that each reactor is required to have, the government steps in and pays it, but the utilities have to pay it back in the future. Whether you want to call it a subsidy or not, I don't know. But in the same building, down on the first floor, is John Wyatt. You can ask him all those questions.
Two more, one here and then there, and then we're going to go.
Could you comment on the importance of thorium in the future here? There's a whole lot of thorium in the world.
There's thorium is another element. It's lighter than uranium. There's thought to be about 4 times as much thorium as there is uranium. Thorium is not fissionable at all. And what you do with thorium is you turn it into a breeder. And so you start up a thorium reactor with something that is fissionable, and the thorium reactor produces uranium-233. Uranium-233 is fissionable, so now you take the uranium-233 out and you use it to refuel the reactor. So you're sort of making a breeder system. Uranium-233 is radioactive. Fuel handling is much more expensive than it is in standard reactors. And uranium-233 makes a better bombs than uranium-235. So taking the balance here, I don't know how to do the balance. People think, and here I agree with them, that the uranium thing is much simpler. If there's enough uranium, India is very interested in thorium reactors, and they are building some. Reason is India has a lot of thorium and almost no uranium. The United States has a lot of uranium and a lot of thorium. Canada and Australia have huge amounts of uranium. I don't know how it's going to come out, but right now the emphasis is on the uranium cycle because of the technical problems with thorium.
One last question.
What are the advantages of multiple cycle or like heavy water reactors over the light water, and then what percentage would you say of the world's reactors are light water, and what sort of impedes their implementation?
Okay. First, heavy water reactors are an abomination and they should all be banned. And I'll tell you why in a minute. I'll tell you why in a minute. Light water reactors are most of the reactors, over 90% are light water. The thing about heavy water reactors is they can run on natural uranium. They are the world's best weapons-grade plutonium producer. They are continuously fueled. Think of a reactor with a bunch of tubes running through it, and I take a ball of fuel and I pop it in one end and another one comes out the other end. If I want weapons-grade plutonium, I make the balls go through in 3 or 4 months. If I want power, I let the balls go through in 3 or 4 years. Monitoring it is very difficult, and they are also, thank God, more expensive than normal reactors, or otherwise we would really be in the soup. So I am not a lover of heavy water reactors, because I think if you're worried about plutonium production and weapons proliferation, they are a big risk. And incidentally, Iran has 3 reactor programs, not 2. One of them is the big one at Bushehr, that's the power reactor. Another one is the research reactor that everybody's been talking about recently. But a third one is a heavy water reactor, 25 megawatts, enough to make enough plutonium for a couple of bombs per year. And that one nobody wants to talk about.
Well, please join me in thanking Bert.
For more, please visit us at stanford.edu.